This Groove tool demo shows the basic functionality of the tool. It is meant for those who have never yet seen Groove in action. At the end of the demo you will understand what graphs and rules are, how rules act upon graphs, and how you can explore the possible rule applications. We will demonstrate this using a model of the famous river crossing puzzle. The puzzle involves a ferryman who needs to transport a wolf, a goat and a cabbage across a river. If the ferryman leaves the wolf and goat alone on one bank, the wolf will eat the goat. Likewise, the goat will eat the cabbage if the ferryman is not present to prevent it. The ferryman's boat can only transport one of the three objects at a time. How does he successfully bring all three across? When you start up the Groove simulator, it looks like this. In order to do anything at all, you first have to load or create a so-called grammar. In this demo, we load the predefined ferryman grammar. The interface is divided into several panels. To the left you see the Rule Overview panel and the Graph Overview panel. This grammar has 4 rules, which I'll explain in a moment. The Graph Overview panel has only a single graph. In the middle you see a display panel showing a particular rule or graph. Right now it is showing the start graph of the grammar. This is a graph representation of the ferryman puzzle. The graph consists of labeled nodes, the rounded rectangles, connected by labeled edges, the arrows. All the essential ingredients of the puzzle are encoded in the graph. Not only the 3 objects in the ferryman, but also the left and right banks, and arrows showing where each of the players is located. Furthermore, there are arrows labeled likes between the wolf and goat, and between the goat and cabbage, representing the fact that one would like to eat the other, though he doesn't dare in the presence of the ferryman. It is interesting to see that the boat itself is not represented in the graph. Because the ferryman and the boat are always in the same position, we can abstract away from the boat and just rely on the ferryman. On the right hand side of the panel window there is yet another panel which shows the labels occurring in the graph. In this demo I do not use this panel, and in fact I can hide it. I'll go back to the rules now. This rule encodes what happens in the graph if the ferryman goes across the river without taking any of the 3 objects across. The colors in the rule are important. The rule can be applied by finding 2 bank nodes in the graph and a ferryman moored to one of the banks. Applying the rule causes the moored arrow to be deleted and another moored arrow to be added to the graph. Thus, applying the rule consists of the following steps. 1. Finding a match for the black and dashed blue elements of the rule. 2. Deleting the dashed blue elements. 3. Adding the green elements. Technically, the black elements in the rule are called readers, the blue parts erasers, and the green parts creators. The Rule Overview panel also shows the existence of a match of this rule. If I select it, the match is visualized. Groove has now switched to a 3rd tab of the display panel, which again shows the start graph, but now certain parts are highlighted, namely the place in the graph where the rule matches. This is called the state view. Double-clicking the match carries through the change prescribed by the rule. The state view has changed and is now no longer the same as the start graph. Instead, the moored arrow is pointing to the right bank rather than the left. This is indeed precisely what the rule said should happen. There is one thing in the rule that it did not yet explain. There is an edge between the 2 banks labeled unequal in C or Java notation. This is needed to make sure that the 2 nodes are matched by different nodes of the graph. Technically, such an edge is called an injectivity constraint. If you have watched the Rule Overview panel, you will have seen that the 4 rules are still there, but the matches have changed. This is because we are now at a different state. You can see this immediately if I select the cross-empty match again. This is how we left the ferryman moored to the right-hand bank, while the objects he has to transport are still on the left bank. The states are numbered on the status line and the tab below. You can see that this is state S1. The start state was numbered S0. The same rule now applies again in this state, and if we apply it, we get back to S0. Over to the second rule. The pattern is pretty much the same as that of the first rule. but now not just the ferryman but also one of the three objects is transported across the river. The object is represented in the rule by the top node. Interestingly, this node is not labeled. The absence of a label in the rule will cause the node to match any of the nodes in the graph, provided it is connected in the correct way to the bank. To be precise, there must be an on arrow from the object to the same bank that the ferryman is moored to. This use of unlabeled nodes is allowed because we are using Groove in untyped mode. Another demo shows the use of typing. On the rule overview, you can in fact see that the rule has not just one, but three matches. These correspond to the three possible objects that can be transported. By selecting the matches in turn, you can see where they are located in the graph, and like before, double-clicking applies the rule at that match. Maybe unlike what you would expect, the object, in this case the wolf, does not actually change position in the graph. Instead, the on edge has switched to the opposite bank. This is quite important. It is the logical structure of the graph that matters, not the layout. I can lay out the graph manually to make it more appealing, but this is not very interesting for the essence of the puzzle. The rule overview tells me that I am faced with three options in this state. The ferryman can cross back alone, or he can take the wolf back, or the third rule can be applied. This rule models the fact that in the absence of the ferryman, wolf may eat goat or goat may eat cabbage. The rule has a red part that we haven't seen before. However, first look at the erasers, the dashed blue parts. This time not only an edge but also a node will disappear if I apply the rule. The node that disappears is the one that is liked by another and gets eaten. The red part is called an embargo or negative application condition. Its purpose is to prevent rule application. If after the readers and erasers have been matched, the embargo can also be matched, the rule may not be applied. The procedure for applying a rule is thus extended with another step. 1. Finding a match for the black and dashed blue elements of the rule. 2. Checking that the red parts cannot be matched. 3. Deleting the dashed blue elements. And 4. Adding the green elements. This particular rule is in fact enabled in the current state. The ferryman is not moored to the bank where the goat and cabbage are located, and since the goat likes cabbage, he may proceed to eat it. The cabbage is gone, and I can no longer solve the puzzle. Fortunately, Groove allows me to retrace my steps by undoing the rule applications. Here we are back in the start state. Of course, it is wrong to take the wolf across. I should take the goat instead. Now I can either go back empty or take the goat back. The second is useless. I'll do the first. If you know the puzzle, you know that I can now take either wolf or goat across without any fear of eating, provided I take then the goat back to the left bank and the cabbage to the right bank. I'm almost done. I just have to go and get the goat. In the rule overview, you can now see that the fourth rule has just been enabled. In fact, this rule does not change the graph at all, it just looks for the structure of the solution. Of course, this solution exists in the state I have reached, since it corresponds to a subgraph. We have now solved the puzzle manually using the Groove grammar. However, the core functionality of the tool is actually to do this automatically. To show this, first I will select another tab of the simulation panel. Here you see another graph, but this one stands for something completely different. Each of the circular nodes here is a state that we have just seen, and the arrows correspond to rule applications that have been explored. I will zoom out a bit to get all of it into view. Zooming in and out is done using the mouse wheel. The green state is the start state, and the blue one is the one that we have just reached. This kind of graph is called a label transition system, or LTS. It represents the state space. For instance, from the start state you can see that we have tried the cross empty rule, which resulted in a cycle. Then the cross loaded rule with wolf, which resulted in the goat eating the cabbage. And finally the cross loaded rule with a goat. which eventually led to the correct solution. In the LTS view, I can still go back and forth in the rule applications and manually try out others. For instance, in this state we have not seen the cross-empty rule being applied. If I now try it, this results in a new transition that is automatically added to the state space. It goes back to a state that we have seen before, namely the one that occurred after we had transported the wolf. Alternatively, I can double-click on the state to explore all possible transitions. You see that these states have now turned white. This indicates that all transitions have been explored. I can always go back to the State tab or Control-click on the state to see it. The real power of Groove is that all of this can be done automatically. I can restart the simulation and then fully explore all states with one click. You see that this state space has 36 states and 89 transitions. The correct solution is the state marked Final, which is over here. The path from the start state to the correct solution can be picked out visually. Alternatively, we can hide parts of the state space. I have now hidden everything except from the trace from the start state to the correct solution. Other demos show you how to use the state space exploration settings or model checking to get much more information about the state space. We'll now show everything again. Finally, another view on the state space is given by the state list in the overview panel. In the state list, you can again select individual states, look at their matches, either in the LTS panel or in the state panel, and also look at the rules that gave rise to the matches. This concludes the demo. You should now have a pretty good idea of the basic capabilities of Groove for state space exploration. Groove away.